In section 2, we learn about the quadratic formula instead of having to solve using completing the square. So again, we're addressing state standard number 8 for algebra 2, and again in the information in the red, we're going to solve quadratic equations by using the quadratic formula today. Apply these techniques in solving word problems, and yes, we solve these equations in the complex number system, so some of our answers may be complex numbers. Now, what we're going to do to begin with is what's called deriving, not to be confused with driving, but deriving the quadratic formula. So we start with a generic or general form of a quadratic equation, some number times x squared plus some number times x plus the constant equals 0. And all I'm going to do is apply the techniques we had yesterday or in the previous lesson to completing the square. So the first thing to do is take the constant, move it to the other side. And that leaves us with ax squared plus bx on the left side. On the right side, that equals the opposite of c. We're going to divide everything in sight by a because this coefficient of x squared is not equal to 1. And so when we do that, now we do have a coefficient of 1 x squared plus b over a times x equals the opposite of c over a. We want to add something here on the left side of the equation to make it a perfect square trinomial. And again, the Texas two-step says we're going to take this number divided by 2. Well, how do you take a fraction divided by 2? Well, instead we multiply by the reciprocal of 2 1/2. So b over a times 1 over 2 is b over 2a, and we're going to square that. So this is a Texas two-step. Take the b over a. Instead of dividing by 2, we're going to multiply by 1/2 and square that. And so what that gives us then is b squared over the quantity 2a squared. So that's b squared over 4a squared. Add that to both sides, and that gives us a perfect square trinomial on the left. So on the left, it is a trinomial. Last one's positive. First one's a perfect square. Its square root is x. Last one's a perfect square. Its square root is b over 2a. And then we take the sign of the middle one, quantity squared. Now, if we multiply these two together to check, that's b over 2a times x, double it times 2. Cross cancels, cross reduces with the 2 in the denominator, and does give us the b over a times x. Right on the left, what we need to do is to figure out how to add the opposite of c over a to b squared over 4a squared. We do that by multiplying top and bottom of that fraction by 4a to get a common denominator. So that gives us minus 4ac over 4a squared plus the b squared over 4a squared that we have. All right, to continue with that, now that we have the common denominator, keep it, add or subtract the numerators. I'm going to rearrange it so it's b squared minus 4ac. We then take the square root of both sides. Doing so, remember the square root of some x expression quantity squared is going to give me the absolute value of that radicand, x plus b over 2a. And that's going to give me the square root of b squared minus 4ac, the numerator, which doesn't simplify any further. But the square root of 4a squared is 2a, and that does simplify. All right, we're going to evaluate the absolute value, and the shortcut we learned was when that's equal, absolute value equals, we can consider the positive 0 negative case by dropping off the absolute value sign and putting a plus or minus in front of it. To get x by itself, we're going to subtract b over 2a from both sides. Now x is equal to the opposite of b over 2a plus or minus the square root of b squared minus 4ac all over 2a. And we notice we have a common denominator. So with that common denominator, let's keep it, 2a, and add or subtract the numerators, the opposite of b, plus or minus the square root of b squared minus 4ac. So that's the process known as deriving the quadratic formula. Your first priority is to memorize the quadratic formula, and we are going to apply it to everything else in the same lesson. Now remember, that started out from ax squared plus bx plus c equals 0, where a could not be 0. That's the general form of a quadratic equation. And if we use this formula, what we want to identify is what a is, b is, and c is. So we have to guarantee that everything is on one side of the equation and 0 on the other. Let's identify that a is 3, that's the coefficient of the x squared term. B is 1, including its sign, so positive 1. And C is negative 1, including its sign. Then we'll substitute A, B, and C into the quadratic formula. So x is not the opposite of b, but the opposite of 1, plus or minus the square root of the entire quantity, instead of b, but 1 squared, minus 4 times a, which is 3, times c, which is negative 1. That entire expression is over 2 times a, which is 3. Simplify that, we'll get our answer. So negative 4 times 3 times negative 1 is positive 12. In the denominator, 2 times 3 is 6. 1 plus 12 is 13. And we don't have any factors of 13 that are perfect squares. So that's in simplest radical form. Again, the fundamental theorem of algebra says we're looking for two solutions. Here they are. And the irrational root theorem says they appear in conjugate pairs. So we have negative 1 plus the square root of 13 over 6. Negative 1 minus the square root of 13 over 6. And that's applying the quadratic formula. So mathematicians decided, rather than completing the square for every problem, if we did it generically with a general form of a quadratic equation, we would get a formula, and if we would substitute the numbers in, execute the formula, we would get our answers. Now in example 2, what's different is we're not ready for the quadratic formula yet. We need to put everything on one side and nothing on the other side. So we're going to subtract 6y and add 3 to both sides. So we'll have 5y squared minus 6y plus 3 equals 0. And now we're ready, and I would suggest let's identify what a, b, and c are. A represents 5, b is negative 6, and c is positive 3. So we're all set to substitute that in the formula. The opposite of negative 6 is positive 6, plus or minus b, which is negative 6, quantity squared, minus 4 times a, which is 5, times c, which is 3. That entire expression is over 2 times a, which is 5. Do some simplification. Negative 6 times negative 6 is 36. Negative 4 times 5 times 3 is negative 60. Denominator, 2 times 5 is 10. Back to the numerator, under the radical sign, the radicand, 36 minus 60 is negative 24, which we're going to have to start simplifying that. If we factor out the square root of negative 1, and 24 is a perfect square factor of 4, and a non-perfect square factor of 6. So continuing on from there, the square root of 4 is 2, the square root of negative 1 is I, the square root of 6 will not reduce. And before we think we are done, there's a greatest common factor in the numerator of 2. If we factor out 2, 6 divided by 2 is 3. 2i squared is 6 divided by 2 is 1i squared is 6. And in the denominator, 10 has a factor of 2 also. And any factor that is the same in the numerator and denominator will divide out to 1. And my two solutions are 3 plus I squared is 6 over 5, and 3 minus I squared is 6 over 5. So the complex root theorem says that if we have one complex root, we will also have its conjugate. And those are the two complex solutions to our equation. All right, now what I would like to do is to take just a moment to read to you a word problem, because we're going to be addressing real-life situations expressed in sentences, aka word problems. This one can be found in your book. It says a swimming pool is 6 meters wide and 10 meters long, and it's to be surrounded by a walk of uniform width. The area of the walk happens to be equal to the area of the pool. What is the width of the walkway? So as we look at this picture here, the rectangle that I've got the blue shading in represents the pool, and it's 6 by 10, 6 meters wide and 10 meters long. Obviously my drawing's not to scale, but we want a walk of uniform width all the way around it, and we don't know what that width is. That's what they want us to find. What's the width of the walk? So I'm calling it X, and it's uniform. So this thickness to the left is the same as the thickness to the right, is the same as the width to the top, the same as the width of the bottom. They're all X. So let's look at this. We therefore know that since the pool is a rectangle, its area is its length times width. 6 times 10 is 60. And from there, what we're going to say is, let's try to find out the dimensions of the walk and the pool together with the walk around the pool. So if this dimension is 6, we're going to add 1x to it on one side, 1x to it on the other side. That now gives me 2x plus 6. And what I have here is the height in this picture. We've got 10 plus x on one side, another x on the other side. That dimension is 2x plus 10. So the area of the entire rectangle with the walk encompassing the pool is going to be 2x plus 6 times 2x plus 10. Now what we know from there is they said in the word problem that the area of the walk happens to equal the area of the pool. So we can write that down as a fact. Area of the pool equals the area of the walk. So what we want to do here, the area of the pool is 60. To find the area of the walk, we can find the entire area and subtract the area of the pool, and that will leave us with the area of the walkway. So the entire area is 2x plus 6 times 2x plus 10, and then we're going to subtract the area of the pool back out from there. So when we FOIL that out, that gives me 4x squared plus 20x plus 12x plus 60, and then we have our minus 60 for the area of the pool. And interestingly enough, the 60 minus 60 cancel out to 0. 20x plus 12x is 32x. To get everything on one side, nothing on the other side, let's subtract 60 from both sides. And what we want to do to make our problem a little easier, and we don't have to, but there's a greatest common factor of 4. Let's factor that out and divide everything in sight by 4. And that gives us a little bit easier equation to work with. X squared plus 8x minus 15 equals 0. That's an equivalent equation. It'll give us the same answers. A is 1, B is 8, C is negative 15. So we're going to forget about the words for a moment and solve the equation using the quadratic formula. So the opposite of B is negative 8, plus or minus B squared, so that's 8 squared, minus 4 times A, which is 1, times C, which is negative 15, all over 2 times A, which is 1. Simplifying that, 8 squared is 64, negative 4 times 1 times negative 15 is positive 60. In the denominator, 2 times 1 is 2. In the numerator, for the radicand, 64 plus 60 is 124. Factoring that out, 124 is a perfect square factor of 4 and a non-perfect square factor of 31. Square root of 4 is 2. And what we've got here is a greatest common factor in our numerator. Factor out the GCF of 2 from the numerator. Negative 8 divided by 2 is negative 4. 2 square root of 31 divided by 2 is the square root of 31. And the factors that are the same in the numerator and denominator will divide out. And what we need to consider is that our two possible answers are negative 4 plus the square root of 31, negative 4 minus the square root of 31. I'm immediately going to rule out this choice because something negative minus something else negative is negative, and the word problem wants the width of the walkway, which is represented by x. The width of anything cannot be a negative number, so let's throw that out. And in order to answer their question, because I'm sure they don't want it left in a simplest radical form, probably don't want to tell the contractor make the width of the sidewalk negative 4 plus the square root of 31. Let's approximate the square root of 31 as 5.6, and we add that to negative 4, and the area of or the width of our walk is approximately 1.6 meters around. So that's our look at how we derived the quadratic formula and to use the quadratic formula to solve equations and to solve word problems.